Welcome to part 2 of airfoils, wings, and lifting things, an introduction of aerospace engineering. This is the second of 3 videos on topic number 7, and we're going to start talking about wings, 3D instead of 2D. Where we talked about 2D airfoils in the last video, we're going to talk about 3D wings in this video. So just stay tuned and we'll start on that in just a second. Before we get going, a quick reminder on our questions. How do we generate lift? We talked about that in the last theory. It's through pressure and shear, no magical dragons. How we relate our forces and moments together, it's those pressure and shear distributions. And today we're going to talk about what is the difference between an airfoil and a wing, and then talk about what happens when we generate a little bit more drag or lift than we want to, or how we can generate more lift and drag and what that means. So on to 3D wings. Comments. First thing we need to think about, airfoils are 2D or infinite wings. They have no tips. They go around. If it was a real airfoil on a real aircraft and we had to be infinite, it would wrap all the way around the Earth. In reality, what we do is we put them in a wind tunnel and they go the whole span of the wind tunnel section. So there are no tips and therefore no tip losses. And we'll talk about what that means here in a second. But there's a property we need in flow and in fluids where the pressures at 2 different points immediately adjacent, infinitesimally small difference apart, have to be equal. Otherwise, we get something called a shock wave. And if they don't, we'll have winds. So they'll equalize. And that's what we get our tip losses. They have therefore uniform span-wise loading. So if I have a wing that's this long, the lift distribution the whole way across it, our airfoil, is exactly the same. In reality, wings are 3D. They are not that. Performance is degraded. Our lift curve slope is no longer 2 pi per radian. It's now less than that. Our CL max at stall is going to be less than our C little L max on an airfoil. And our CD is the actual CD for our wing will be greater than our airfoil CD. Everything gets worse. We also add a couple more shape parameters where before we talked about chord and mean camber line and our other geometric envelope, we now have our span, which we represent as B, our Oswald's efficiency factor, or E, and that's a function of how close to the ideal span-wise lift distribution we have. Aspect ratio, AR or A, which is technically B over our mean structural chord, or for most wings that are tapered and swept, it's much easier to do B squared over our planform area. And then our taper ratio, which is just the ratio of the chord of the wing at the tip to the chord of the wing at the root near the fuselage or in the center of the fuselage, depending on your definition. A little word of warning here. There are different conventions for calculating S and C root. So be very careful when comparing wings and wing areas from different manufacturers and different places. For instance, Boeing and Airbus use 2 different methods to calculate wing area. And as such, their information is not directly comparable. Once you understand the difference, you can calculate the different relative wing area. It's off by several percent, and you can then compare CD to CL and L over D max and stuff a little bit more readily between the 2 manufacturers. Okay, so again, our wing definitions for our pure rectangular wing, like this, also known in America as the Hershey bar, after the famous chocolate bar in America wing. A is just B over C. And in this case, because it's an ideal wing like this, it's not just C bar, it's something we call our mean aerodynamic chord because our chords are all the same. We're going to talk a little bit more about mean aerodynamic chord, but just before we get to that, remember an aerodynamic chord or mean aerodynamic chord is not the same as mean structural chord, and that's just due to the aerodynamic effects of having a 3D wing. If we have a tapered wing where we want to use B squared over S, we have our taper. And as you see, the C root and the C tip. Interesting thing is I've drawn an elliptical wing on here. And the reason I draw an elliptical wing is in the ideal sense, an elliptical shaped wing produces an elliptical lift distribution, which is ideal. That gives us this efficiency factor would be 1. In reality, because we put a fuselage or other things on our wing, or there's dirt or dead bugs, an elliptical wing never generates an ideal elliptical lift distribution. And therefore, our efficiency factor is going to be lower. In fact, it's generally in the 70 to 90% range. So think about that. elliptical wings are ideal, but they're not realizable in reality. And therefore, it's actually often better to just have a simple rectangular tapered wing or a slightly curved wing to get that ideal or closer to ideal lift distribution. Okay, remember we had our drag polar, which is CD, and it is a function of CD naught and CL. And we now go from little d to big D. CD naught is the drag at zero lift, technically. And then this K is a function of our wing shape and CL squared. We can estimate K in this case is 1 over pi times the aspect ratio times the efficiency factor. So the lower, the smaller our K, all else remaining equal, the more efficient our wing is at generating lift for each unit of drag. And the lower our CD naught is, the more efficient our wing is at cutting through the air, even if it generates no lift. What that means is our wing gets more efficient as our aspect ratio goes up and as we get closer to that ideal elliptical lift distribution. We also then have things with tip vortices and downwash, and that's in this relationship. It's the tip vortices and downwash that give us our 3D drag polar. So anytime you hear the word drag polar, think of this equation. This is a simplified representation. There's also a CL term. There may be CL cube terms and other terms in the drag polar, but we tend to use this simplified representation. CD equals CD naught plus KCL squared for most of what we do and most of what you're going to do this year and next year in aerospace engineering. Okay, this is what our lift distribution looks like. Now, remember what I said about it. The pressure on the lower surface and the upper surface at your tip has to equal each other. Otherwise, you're either going to have flow that moves up or you're going to have a shock wave. And as such, because the pressures have to be the same, you cannot generate any lift at your wingtips. So you're always going to go to zero here. You tend to be maximum, and you want this to be as smooth of an ellipse as possible. And that's what your E is how close you're getting to that ideal sense. But because of that, because you have some high pressure here and lower pressure here, this flow wants to move like that and curl around the tip. And that's what we call a span-wise flow or span-wise thing. And it gives us our tip vortices. And those tip vortices can be thought of as two things. One is you're taking energy that would normally be used to generate lift by moving downwards to generating a vortex that trails the aircraft. So that's losses in energy. That's drag for no lift. It's the L over D. Your lift to drag ratio is decreasing. It's also those vortices are high energy flows that will disturb trailing aircraft. So you hear about wake vortex interaction in aircraft, and it's interacting with those tip vortices. And keep in mind, those vortices form anytime you have a break in lift. So it could be your wingtip, it could be a split in a flap. You know, the flap runs along your wing. Anywhere along the wing where the lift changes abruptly, you'll get a wingtip or tip vortice, and that's what you get. Okay. So remember we set our lift curve slope for our 2D airfoil, thin airfoil is approximately 2 pi. And that means our CL is 2 pi alpha, where alpha is in radians. For 3D slope, for a thin, medium to high aspect ratio, untapered wing, we can use this form. Now, as we add tapering, or we add sweep or any of that, that will change, that will further reduce the slope. But as you can see, our 3D lift curve slope is always less than our 2D lift curve slope. If we go to an infinite aspect ratio, that drives this to 0, then they're 1. They're the same. So that's our 3D to 2D transition. Okay. Now, remember we talked about aft-loaded or supercritical airfoils in the last video for flying closer and closer to the speed of sound. The other option, or one of the other options we have for a wing, is to sweep it. We actually tend to use both together. So if you go look at an A320, a 737, they have a wing sweep. 747, 787, A350 are swept even more. And that's because they fly close to the speed of sound. And what we have is this is big lambda instead of little lambda, and it's just the angle of sweep. And what that means is that our wing, which sees the normal velocity, so if our velocity is moving down like this, it just reduces the normal component to the wing. And we can define this as both leading edge, trailing edge, and our lambda or quarter. And it reduces that normal velocity, reduces the drag we generate for a given Mach number that we're flying at. But part of the problem is it now causes span-wise flow. For aft swept wings such as this, the flow moves from the root towards the tip. And for forward swept wings, it moves from the tip to the root. And that changes the behavior of the wing. In an aft swept wing, it makes it's more likely that will have a higher angle of attack towards the tip, and our tips will stall first. And that causes two problems that we don't see in a straight wing. One is if this tip stalls before that tip, we get a rolling moment. So it means when we stall an aircraft like a 737 or an A330, we can get quite large excursions in bank angle. And if you look at the flight data recorders from Air France Flight 442 over the South Atlantic before it crashed on its way from Rio to Paris, you'll see that at some points they were 60, 70, 80 degrees bank angle. It also means that effectively this part of the wing stops generating lift before this part of the wing. And that moves our aerodynamic center, our neutral point for our aircraft forward, which makes it less stable as we get to higher angles of attack, which means in some respects, our elevator, the behavior of the aircraft changes. And why this is important is all swept wing aircraft have this problem, be it from the original 707s to the modern A350, A320, 737, 787. And it's how we deal with this that matters, hence the 737 MAX accidents. So I would like you to think about how that behaves and what that means. This is a combination of this topic and topic number 5. Okay. For forward swept wings, what happens is because this area stalls first and that these generate higher lift and more readily, and they tend to pop off. Our wings actually want to break off, which has always been a challenge. Another thing we can do is we want to reduce those tip vortices. So ideally, we just extend the aspect ratio, extend the taper, but that's two problems with that. One is it takes up more space on the ground. And as you know, airport gate space and taxi space is limited. And two, it makes our wing heavier. So what we do is we do a compromise. We use a winglet, which we change the direction of the wing at the tip. You see it goes up, and that's the typical upward winglet, or we can have a downward little winglet, what we call a split winglet or a scimitar winglet. And both of those, they increase the effective aspect ratio of the wing without increasing our span. And as such, the tip vortices are reduced, the losses are reduced, and the aircraft generates more lift for a given amount of drag. Now, a couple of comments on winglets before we get there. You normally see upward facing winglets, and those are really useful because they're less likely to strike the ground. Unfortunately, they're actually the less efficient. This downward winglet you see here actually generates a much better return for the same area and same weight as an upward winglet. So you're seeing that on the new 737s that are being retrofitted next gens and on the 737 MAXs. The consequence, of course, is that this is more likely to be damaged in a wingtip strike. The other thing about winglets is it changes the profile of lift and twist and bending near the tip. And it means that very often we have to put ballast on the wing to make sure the wing remains structurally stable near the tip, because obviously we don't want the wingtip breaking off. That would be bad, but it reduces our tip losses. Okay. That brings us to the end of the 3D wing discussion. In the next video, we're going to talk about lift alteration devices, i.e. flaps and slats and the like. So stay tuned for that, and thank you very much.